All right, so we are looking at Journal 37, and we're going to start out with a bell work here. As you can see, this bell work is dealing with cubic functions. Also, I want to mention in the background, if you hear any like rumbling noise, it's just my dryer, so excuse that white noise right there. So let's get started. All right, so looking at this here, let me grab a pen. Let's talk about finding the vertex for a cubic function. Notice that this is a function to the third power, so this is a cubic function. And if you remember that this is in vertex form, in other words, in the parentheses here, it tells us our shift that tells us left or right, and outside here tells us the shift that is either up or down. So if it's a -2, so minus sign means that it's shifting right. So right 2, and the plus sign on the 3 means that it's shifting up 3. So let's go ahead and draw that or plot that point on the graph. So right 2 up 3 is right here at 2, 3. So I'm going to write that coordinate on the vertex. I'm going to put a little V here to help me remember that this is the vertex when I am drawing my curves. Okay, so next thing I'm going to do is actually plot the other points. Remember, if this is a cubic function, we need 3 points to plot a cubic function. So we need 2 more. How do we get it? Well, we get it by getting the slope of this function. The slope of the function is the number in front of this x. So right here, it looks like the slope is 1. So if my slope is 1, I can always write that number over 1. So this gives me my rise over run. All right, so from the vertex, we're going to go up 1 over 1 because our slope is 1. How do we get our third point? Well, you just take your slope and the vertex and you go the opposite direction. So remember how we went up 1 over 1? Well, now we're going to go down 1 to the left 1 and plot our point. Next, we're going to connect the dots. So from the vertex, I'm going to swing it up, and then I'm going to swing it down. And so there we have it. We have our graph. Now we're going to find the other 3 components. Let's start with the y-intercept. Now, a y-intercept is just a coordinate, right? So for a y-intercept, the x value is always 0. Now we just have to find the y value. So let's do some math here. So y, plug in 0 into this equation, 0 minus 2 cubed plus 3. And we're going to work this out. Remember, parentheses first, so we're going to work inside the parentheses. So 0 minus 2 gives me -2 cubed plus 3. -2 cubed, well, that's just saying -2 times itself 3 times. So -2 times -2 gives me +4. +4 times -2 gives me -8 plus 3. And if I were to add this up, I get -5. All right, so that means that my y is -5. And if I look for, so that's my y-intercept. So now I'm going to go ahead and find my domain and range. So for domain, we are going to be looking at the x axis and see how far that this curve stretches to the left and stretches to the right. So we can see as we extend this side of the curve, the left side of the curve, on and on forever, it's always going to keep extending left. Same thing for the right side. It's always going to be extending right. If I were to kind of curve this out, if I were to zoom out. So in this case, we are going from, I'll write it down here, -infinity to +infinity, right? And how do we represent this symbol? Well, we use that fancy R sign, meaning all real numbers, because all x values are included here. So in this case, all real numbers for the domain. And for the range, we're looking for the specific, really for the y value. So we can see that we have to ask ourselves, what's the lowest y value that this curve can be? And as you can see, it's always extending down. There's arrows here. So it's going on and on to -infinity. Whereas the other side, it's extending on forever upwards, so it's going to +infinity. So we're going from -infinity to +infinity. That means that the range is also all real numbers. So on here, I'm going to write all real numbers. And if you remember from last semester, a cubic function's domain and range is always all real numbers. So now we have our everything completed. So I'm going to pause here. All right, so now let's talk about graphing square roots and cube roots. So if you take a graphing calculator and you were to plug in this function, you are going to get a graph that looks like this. So for a square root graph, it looks like kind of like a hill or like a trajectory, you can think of it, where the starting point, what we call the vertex, starts at the origin. So for the vertex, it starts at the origin at 0, 0. So that one is for the square root. Now for the cube root, if you plug this into a calculator, you're going to get something that looks kind of like the square root function, only it has, the curve goes on the right and the left. So it looks like this, where the vertex is the middle point of this curve. And this is also the origin. Okay, so let's take a look at the differences between a square root and a cube root. So a square root doesn't have like a number above it, right? Whereas a cube root has a 3. So just be aware of that. This one's a square root, this one's a cube root. And the picture looks different. Let's talk about the y-intercept. So where does this graph cross the y-axis? Well, it crosses it at the vertex, the same point at the vertex, right? Which is going to be 0, 0. And for the cube root function, it also crosses at the origin for the y-intercept. So I'm going to put 0, 0. So both of these are crossing at the origin for the y-axis, for the y-intercept. So let's take a look at the domain and range, because this part gets a little interesting here. So if you look at the square root function, notice that it's only on the right side of the coordinate system. Like, why isn't it drawn on this side of the coordinate? Well, let's just think about how square roots work. So square roots, let's write this up here, square root of 4. If I were to plug in any number into this x, like the square root of 4, let's calculate that. That's just 2, right? So if I were to kind of plug in 4, which would be like maybe say right here, and plugged it in, I get maybe 2 above it, like on the curve. Let's say I were to plug in 1,000,000. I can plug in 1,000,000 into a square root, right? And get some number. It'd be a really big number, but I would get a number. So as I plug in numbers, positive numbers, into this square root, I'm going to get a number, and as the numbers get bigger, the square root of that value gets bigger. So this is growing slowly on upwards. But why is it that this side doesn't have anything here? So let's go back to understanding. Let's start at the square root of 0 right here, right? So the square root of 0 is 0. And so that's why the vertex starts at the origin. But let's think about what the square root of a negative number is, because these x values over here are negative. So if I were to plug in a negative value in here, like square root of -1, what does that give me? Well, if you remember, back in the first semester, we learned that you can't take the square root of negative numbers because it gives you an imaginary number, right? And we can't see imaginary numbers, which is why we don't see anything appearing on this side of the coordinate system. So that's why this square root the curve is one-sided. So now that we know why that picture looks like that, let's talk about the domain. So the x value that it starts at is x equals 0, and it goes on to x equals infinity, right? Positive infinity. So the smallest x value here, or the furthest x value to the left, is 0, and as you go more to the right, it's going to positive infinity. So on here, I'm going to write 0 to positive infinity, always parentheses on infinities, and we're going to use a bracket on the 0 because it actually touches it at x equals 0. Notice it's a closed dot. Let's talk about range. So for range, we're going from the lowest y value to the highest. So looking at this curve here, the lowest y value is here. That's the lowest point. So that y value there is 0. As you increase further up, this y value is increasing on forever and ever because of this arrow. So we're also going from 0 to positive infinity and parentheses and brackets. For square roots, you're always going to need a bracket on the number. So just be aware of that. And by the way, domain and range are not always going to be the same for square roots. It just happens to be that case in this problem. Let's talk about domain and range for the cubic function. So for the cubic functions, as I'm going left of this curve, notice that it's continuing on to go further and further left, right? So we're going to negative infinity when we're doing that. And if I go to the right of this curve, I'm going to positive infinity for the x-axis. So we're going from negative infinity to positive infinity. In other words, this is going to be all real numbers. I'm going to use that R symbol instead. Let me erase that real quick. Oh, that's weird. Why is it not erasing this guy? Okay, ignore that, but I'm going to write all real numbers. Just scribble that out. And all real numbers for the range, because as this curve is going down, it's also, as it's going to the left, it's also going down, right? So the lowest y value is going to be negative infinity, and while the highest y value, this is always going up. So it's going to positive infinity, so it's all real numbers for the range as well. So I'm going to pause here. Also, I want to mention, this part is really important. For square roots, you can't plug in a negative number. As we can see here, we got imaginary numbers. But for cube roots, notice that the curve does appear in the negative region because you can plug in negative values into cubic root functions. Let's think about it. So we know that negative 8 let me rewrite that. Negative 2 to the third power is negative 8, if you remember from the bell work. So if I were to take the cube root of negative 8, I should get negative 2 because cube roots undo cubes, taking the power to the third power. So in this case, the cube root of negative 8 should be negative 2. So on this graph, we have that's why we can take negatives, numbers of cube. So we can take the cube roots of negative numbers. So just again, let me just reiterate. Square roots, you can't take the square root of negative numbers, whereas cube roots, you can take the cube root of negative numbers. So just be aware of that. All right, now let's just tie in how to find vertexes for all given roots. Now, in the previous slide, you might have noticed that there weren't any shifts in those roots. But let's talk about when there are shifts. So looking at this equation here, let's talk about three components, this a, the negative sign, and the positive sign here. So the signs on the inside of the square root tells us, you might already can guess it, just like the bell work where the inside the parentheses, a negative means right shift. Well, a negative on the inside of a root means a right shift, whereas positive means left shift. A positive on the outside of the root means up, whereas negative means down. And this a, which is right in front of this x on the outside, is a constant. And because it's next to this x, it is the slope. Okay? And now, let's talk about why I put this like box here. So this box is just to indicate that this template or this formula here is for all cases for any roots. In other words, this could be a 2 here, which would refer to as a square root. If it was a 3 here, it'd be a cube root. If it was a 4 here, that means that it's taking the 4th root. And you can see I can go on and on forever. I can go to the 100th root if I wanted to. So that box is just there so that this is referring to all root cases. And then let's talk about what the vertex would be. So the vertex here is going to be HK, right? Because H tells us how many units we're going right or left, whereas K tells me how many units we're going up and down. Okay, so let's use all this notes here, all these skills here to help us graph some square root functions and some cube root functions. So please watch the videos for that. I'm going to be doing some example problems straight from the homework.